space. If it's a two-dimensional abstract space, how many basis vectors are there going to be?
2.
So there's going to be 2, like I hat and J hat in a vector space, right? So in this one, a very original name of 1 and 0. That's one of the bases, one of the base cats. And the other base cat is this. Are those Yeah, I mean, just like in vector space, those span the 2 dimensions, okay? Are these normalized, by the way? Are those 2 base cats normalized? They're not?
They're 1.
Are these basis sets, right? Base cats normal. Is this base cat normalized?
It's 1.
Sure it is.
Yeah.
Is this base cat normalized?
Yes.
Sure it is. Okay, good. All right. So we have a nice normalized base cat. This is like our, you know, when we were solving the Schrodinger equation, we did separation of variables, and we got the nice infinitely dimensioned basis set that was orthonormal and all that. All right. By the way, is this orthonormal? Does this have all products in function space and vector
Yes.
space? Okay. So it's a good starting point. All right. But it doesn't, and what we did is maybe associated this with an electron neutrino and associated this with a mu1 neutrino. Okay, I'm not going to go through every detail because we did this problem in great detail last week. All right, so what we did is this, is we said, what Griffiths uses a different letter, all right, he uses S, but I'm a creature of habit, and so I say psi general, but he used capital S, equals some linear combination of A times 1 plus B times 2. Where again, I'm going back to the idea that psi general equals summation over n of Cn sine n. You know, that type of idea. And if I made it, and it's no big surprise, if I made it time dependent, then I would slap on e to the minus I E n over h bar t, right? So this is no different than what I just did right there. Everybody kind of agree? It's what we've been doing all along?
Yep.
Yeah? Okay. All right. So what we did is we started off with, we were given a problem. Okay, that for these, in this case, the electron neutrino and the mu1 neutrino, there existed a Hamiltonian. And that Hamiltonian matrix form equal HG, GH. All right? So the first thing we want to ask, is that Hermitian?
Yes.
It's Hermitian, all right? So, you know, the observables that we're going to get observables for it. We're going to get real eigenvalues, all right? Which means we're going to get real observables, and so these are things we can measure, all right? And so the Hamiltonian is given this. So the next problem is to solve Schrodinger's equation. All right? And so Schrodinger's equation looks like this. H times psi equals IH partial psi with respect to t. But what do we always do?
Separate.
Okay, so let's get rid of the time dependence. So G of t equals e to the minus I E n over h bar t. And what are we left with? We're left with this, but instead of solving it as a differential equation, we're going to solve it as in this abstract space. All right, and so what type of equation is this called? It's Schrodinger's time-independent equation, but it's an eigenvalue or an eigenfunction equation.
Yes, eigenfunction.
All right, so what happens is that gives us a little bit more insight of what we were doing when we were doing Schrodinger's equation. You know, it's not so easy to see that it's an eigenfunction or an eigenvalue equation when we're doing the differential form of it. All right, but when we're doing the vector space form of it, because we recognize the rotations and everything like that, it's far easier to identify this is an eigenvalue problem. Okay, and so what do we have to do for this? We have to solve it, right? And just like we always do, we solve for the size, the cats, all right? And what will those cats form?
Complete basis set.
And they'll form a complete basis set. All right, now, one thing that you should have thought about is, well, we started off with this two-dimensional space. But does that two-dimensional space automatically form the the eigenbasis of the Hamiltonian?
Not necessarily.
No, not necessarily. So what we're going to do is we're going to build the eigenbasis, and it's going to be built out of this original basis that wasn't the eigenbasis of the Hamiltonian. All right, so what we did here is we solved this problem, h minus 1, this is my matrix 1 times E times ket psi equals 0. And what's the only way that this can be true?
If it doesn't have an inverse matrix equals 0.
If it does have an inverse matrix equals 0.
It does have an inverse matrix
Right.
equals 0.
No, wait a minute. If it doesn't have an inverse matrix,
It's true.
which means that its determinant equals 0. Okay?
Determinant.
So what we need is we need the determinant of this thing to equal 0. So we need the determinant of h times 1 e to equal 0. And when we write that, we get the determinant of h minus lambda, or let's do it this way, e, g, h minus e equal to 0. And when we solve for this, do you guys remember how to take a determinant in general? This is a two-dimensional determinant, so it's easy.
H minus E squared.
Okay, so it's easy in two dimensions. What if I have a 3 by 3?
Yeah, then
You cross up and you hold the
set
center.
do the cross product.
So what you do, you find the easiest row, right? And the easiest row, the one that has the most zeros. And then what you've got to do is you've got to start with, here's a complete side note. A, B, C, D, E, F, G, H, I. The determinant of this equals what?
Would be A, E, C,
A times
Minus
EC minus
HF,
minus HF. Plus or
minus B,
minus B.
DC, minus FG.
So I go like this. So this is what I do for B.
Yeah,
You cross out this and you
Yeah.
cross out this.
DC minus FG.
DI.
Oh, is that
It's
9?
not, yeah. DI
DI
minus
minus
FG.
Sorry.
Yeah, that was
Plus
minus
C
plus C times
times DH minus EG.
DH minus GE. Very good. Okay, that's how you solve for the determinant of a three-dimensional one. And in general, what happens is plus this number, minus this number, plus this number, but what about this one?
You don't have to reverse the sign on the B if you just flip the
Okay.
DI and FG.
I'm not going to go there. I'm going to keep this general form. I agree.
Minus plus.
It's minus, yeah. So what happens is, generally speaking, if this has, if, for example, say it was this, what would the determinant of that matrix be?
Well, B1 0.
E times
A, So what I do is this, you choose this row, and I kind of do this. So it'd be, I would do the first one, would be 0 times that determinant, then it would be E times that determinant, then 0 times the other determinant. But because I have two zeros there, that's the easiest row to choose. So the whole deal to calculate the determinant of a 3 by 3 is to, find the nicest row. And the nicest row is the one that has the least number of zeros. All right? And so this all should equal, well, this is a different problem, but over here it would be, so it would be 0 times EI minus H0 plus, it would be minus that one, right? Because they have minus and then plus E times, so then I would do this, AI minus GC, and then it would be the next one, which would be minus 0 times
Wouldn't it be
0
negative 0 minus times BI not?
Yeah, I screwed up here.
This would be BICG, shouldn't
So
it?
BI, yep. DI, so wait a minute, 0 this way, BIHC. All right, and that goes to, but long and short of it, that goes to 0, and this is the determinant right there. All right, Eric, you look perplexed. You haven't seen this before?
No, I've seen it before. I'm just
Okay.
gonna bang my head against it again, I guess.
Okay, yeah. Okay. Here's the scoop, guys. I think I asked you guys, well, maybe I didn't ask you guys to do it. But what I did is I went home and I did this problem using Maxima. All right, and so do this problem doing Maxima. All right, I would like you to do it by, if it's a 2 by 2, I want you to do it by hand. Got it? There's no reason you can't do a 2 by 2 problem by hand. But if it becomes 3 by 3 and greater, then maybe do it in Maxima. All right, so in order for me to do a greater than 2 by 2 problem Maxima, what I did is I went and I checked my 2 by 2 problem in Maxima. All right, and so in Maxima you can, put in, enter a matrix, and then once you enter a matrix, you can say eigenvalues, and it will give you the eigenvalues, and then you can put in eigenvectors and you get the eigenvectors. So I want you to be able to do that. All right, and I may even for the test on Tuesday have these computers on so that you'll have access to Maxima. All right. Okay, but that's a side note here. Let's get back to the problem.
And what was the rule in order for that to work? It was the inverse of,
It's for this thing. Let me call that A. All right. For A to not have an inverse, it has to be true that the determinant of A equals 0.
and you're calling A what?
This whole matrix.
The difference of those two?
Yeah, I didn't want to write that again. Okay? Okay, so we did this. And what do I solve for from here, guys? This has gone much slower than I didn't even review this. What do I get from this? What do I solve for here?
You want to get h minus e quantity squared minus b squared.
No, what are the answers? I'm not going to do that. What am I looking for? What can I pull out of this thing? The e's, and what are the e's? Those are the eigenvalues. So what I do is I pull out 2 eigenvalues. I think he calls them E plus and E minus. What is E plus equal to?
H plus g.
H plus G, and then E minus equals?
H minus g.
H minus G. All right, so I have 2 eigenvalues. Now for each eigenvalue, I can find an eigenvector. Right, these are the eigenvalues. And then we went over how to find the eigenvectors, right? This is one of the last things I did. We solved the eigenvectors. I'm sure I did. All right. And what did we get for the eigenvectors?
Plus or minus 1 over square root.
Okay, so let's just say this. Let's call our psi plus equals 1 over the square root of 1. Is that right? Yeah?
Yeah.
And then psi minus equals 1 over the square root of 1 minus 1. Okay, what does that mean that I found this eigenvalue, this eigenvector, this eigenvalue, this eigenvector? What does it mean?
You have 2 different possibilities.
Okay, yeah, let me ask you this. What does it mean in terms of an operation I can do with a Hamiltonian? So what does it mean? If I write H,
It's like raising and lowering operators?
Nope.
No, you have 2 different basis sets.
Okay, so how about this? What does this mean?
That means a Hamiltonian
plus.
is standing up.
Okay, no, I mean, let's think about just in terms of
You
what I
have
have
E
here.
plus,
I have E plus,
and then you have psi plus.
psi plus, which I can rewrite as H plus G, psi plus. Right? So, let me ask, is this an eigenvector problem?